right, welcome. Today, we are going to dive into one of the most mind-bending, rule-breaking ideas in all of physics, quantum tunneling. Seriously, it's a phenomenon that acts like a cheat code for the universe. And believe it or not, it's happening all around us, and even inside us this very second. So let's figure out what that actually means.
So let me start by asking you a question that seems, completely obvious. Can something pass through a solid wall if it doesn't have enough energy to just smash through it or climb over it? In our everyday world, the answer is, of course not. No way. But down in the quantum world, the answer is a fascinating maybe. Think about it like this. In the world we see, the rules are clear. You roll a ball up a hill. If it doesn't have enough speed, it's going to roll right back down. Simple. It can't just magically appear on the other side. But in the quantum realm, tiny particles like electrons, well, they play by a totally different set of rules. There is a small but very real chance they can just pop up on the other side. They literally tunnel through the impossible. And look, this isn't just some weird little exception to the rule. This is a fundamental feature of reality itself. It forces us to completely rethink the basic laws of physics we thought were set in stone. So here's the official definition for you. Now, the key thing to get here is that the particle isn't like finding a tiny crack or drilling a hole. This bizarre ability comes from the very nature of matter at this tiny scale, where things are less like solid objects and more like waves of probability. Right, so to really get our heads around how this is even possible, we have to stop thinking about particles as these little solid billiard balls. Instead, you've got to start picturing them as fuzzy, spread out waves of probability. And once you do that, the way they interact with barriers changes completely. Okay, so here's how it works. It all starts with something called the wave function, which is basically a map of where a particle might be. Now, when this wave hits a barrier, it doesn't just splot against it and bounce off. A part of the wave actually leaks into the barrier. The wave gets weaker and weaker really fast inside, but, and here's the kicker, if the barrier is thin enough, a tiny bit of that wave can make it all the way through to the other side. And if the wave is there, there's a chance the particle is there too. So what decides if this impossible jump actually happens? Well, the number one factor is the thickness of that barrier. The thinner the barrier, the higher the chance of tunneling. It's that simple. Now, the particle's mass and the barrier's height also matter. Lighter particles and lower barriers make it easier. And that right there is why we see this happen with teeny tiny electrons all the time, but not with, me trying to walk through a wall. Now, you might be thinking this all sounds like some wild abstract theory, but it's not. In fact, back in the early 20th century, quantum tunneling was the only thing that could explain a huge mystery at the heart of the atom. For years, physicists were completely baffled by radioactive decay. They knew that certain atoms could spit out these things called alpha particles. But when they did the math, they realized these particles were trapped inside the nucleus by a massive energy wall, thanks to the strong nuclear force. There was just no way they should have had enough energy to escape. Yet they did. And then came the breakthrough. In 1926, Erwin Schrödinger published his famous equation that described particles as waves. And just 2 years later, a physicist named George Gamow had this incredible aha moment. He realized the alpha particles weren't blasting their way over the barrier. They were tunneling right through it. It was one of the first huge wins for the new, strange theory of quantum mechanics. Okay, so tunneling explains something about radioactive atoms. That's neat, I guess, but why should you care about it today? Well, it turns out this little quantum cheat code is basically running the entire universe in ways you would never, ever expect. I just love this quote because it really gets to the heart of it. This isn't some obscure fringe effect we're talking about. It is absolutely fundamental to, well, everything. Let me just give you a few examples. Just look at the range here. In stars like our sun, protons don't actually have enough energy to get close enough to fuse together. They have to tunnel through that barrier of repulsion. That process powers the sun and created pretty much every element heavier than hydrogen. And then, in your smartphone, tunneling is what lets electrons be written to your flash memory. It's how we see individual atoms, and it might even be happening inside our bodies. Just let that sink in for a second. The same weird quantum rule connects the nuclear furnace of a star to the data on your phone and to the very chemistry of life itself. It's all particles taking a leap of faith through a barrier that should be impossible to cross. And speaking of seeing atoms, that number you see there, that's the kind of precision we can get with a scanning tunneling microscope, or STM. It works by measuring a tiny electrical current of electrons that tunnel from a super sharp tip to a surface. That current is so incredibly sensitive to distance that it lets us map a surface with a resolution of about 1% of an atom's diameter. We can literally see atoms because quantum tunneling exists.
And if that's not crazy enough, check this out. It's an idea from the field of quantum biology. The two strands of your DNA are held together by hydrogen bonds, and there's a proton sitting in there. Well, scientists think that sometimes that proton can tunnel to a different spot. And if that happens right before your DNA copies itself, it can cause a mistake, a spontaneous mutation. Tunneling might actually be one of the engines of evolution. So let's just step back and pull all of this together. What is quantum tunneling really telling us about the universe we live in? What this all really shows is that our common sense view of the world, a world of solid objects and absolute rules, is just a good enough approximation. Down at the fundamental level, the universe runs on probability, not certainty. A barrier isn't a no, it's a probably not. And that tiny subtle difference is responsible for, everything, from stars and technology to maybe even us.
And that leaves us with one final fascinating thought. We're already using this quantum cheat code for so much, but we're just scratching the surface. From building hyper-efficient electronics to maybe, just maybe, unlocking the secrets of quantum computing, this bizarre quirk of the universe is still packed with potential. So the only real question is, what impossible barrier will it help us cross next?